Hello again. Thanks for staying here, and hopefully we are going to manage through the next approximately 1 hour of, I hope, not so dull presentation, and that you are not going to fall asleep if you're not sleeping already. So I can boo you once or twice or 3 times so that you are fully awake and that I can proceed. So the title is a little bit provoking. The question here, of course, is whether the software stack can be big. Yes, of course. Can it be fat? What does it mean? It means that it has a lot of layers. It has a lot of complexity. And can it be safe? Now, this is the question that most of us ask ourselves these days, and while developing solutions for different safety critical systems, being that autonomous cars, what we are all awaiting. And this topic is going to be targeted, and this talk is going to be targeted to the field of automotive. So this is the target. So let's see how it goes and how it goes in the world of functional safety. Do I have the control to control the slides? Probably yes, or maybe even not. Okay. It is good that the session chair at the conference chair can experience the same problem as the participants. So this is the good thing. I think that you also cherish the possibility to see let's say the overall UX of the conference and not only the presentation, so that it can be okay. Okay, so now, where the software comes into interplay with cars. So this is the first question that we need to ask ourselves. So software versus cars, and cars versus software. So traditionally, of course, cars were something like this. So this is the traditional vehicle architecture. Even today, many vehicles have a dozen of different components and subsystems. These blocks here, these little boxes, are the electronic control units here that control some specific parts in some specific area of the car. So we see that these green parts mostly control the steering, braking, and actuation in the car. So we have the powertrain controls, airbags, gears, engine, steering, etc. We have here different infotainment and comfort related functions, being that the GPS, HVAC, video, audio, radio, hands-free calls, head-up displays, etc. And now when we want to have some autonomous functionalities, we need sensors, we need telematics to be able to position the vehicle within the field. We need the updates, of course, for the software. We need some gateways there. And of course, we need to control the car body, like via the door nodes, via the, let's say, a body control block, headlamps we want to control, etc. So this is, of course, a very, very complex architecture that we need to manage somehow and to interconnect via a variety of protocols, being that CAN or LIN or FlexRay or more recently Ethernet, and for video we have LVDS. And now when we take this figure and make a mind map and say, okay, this is the figure that we have, this is the architecture of the car, and now we get the request for autonomous mobility. So how it goes from there? What about the complexity? How we manage the complexity and how we create a solution for autonomous cars based on all these blocks? So we definitely need to update the architecture. So we cannot sustain the previous model because the complexity is that big. So we need to compact the design a bit. So currently we have a lot of developments dealing with those blocks. So we have powertrain controller, driving assistance controller, digital cockpit controller, sensors, and here it should be actuators. Somehow it didn't paste in. Anyhow, these controllers are called domain-specific controllers or domain controllers, in the words of tier ones and OEM companies in automotive. Why do we compact these domains? Because in every of the domains, we can then use less hardware, in fact, and the hardware will be more compact and integrated, and we use more software to define how these blocks shall work in a software way. So software-defined vehicle, as it was software-defined radio, software-defined this, software-defined that, is something that we also want to achieve in the field of cars. And Yeah, for me, as I wrote in the abstract, it was pretty cool. Yeah, it gets integrated even to the point where we have a central vehicle computer, like one big computer for the whole vehicle. I have sensors and I/O, I have actuators, all connecting into the central vehicle computer. All of a sudden, I'm back at the second year of the studies where I have a simple autonomous system block diagram. And it seems really simple. It seems really simple. However, now my experience needs to come into this. How? This central vehicle computer, I need to model. I need to model the architecture of it, and I need to play around with hardware and software architecture. And this is what I like the most. So let's see. How can I design the central vehicle computer? So this is an excerpt of what could be a design of a central vehicle computer. Different companies do this in different ways. This is, let's say, one of the most common takes on this. So we have what is called a main chip. This is a master chip. Sometimes they call it a high performance controller. So this is basically an SoC, system on chip, a silicon that has multiple ARM processors of different kinds, has accelerators, DSPs, multiple DSPs, have some vision engines, also some AI acceleration blocks. They call it tensor processing unit nowadays, units, and they have, of course, CPUs, different CPUs. And this is a great field to play if you are a software guy. So you need to provide an environment in which to run different applications. So you start and see, okay, what I have on the disposal, what is the hardware I/O, which interfaces I have on the disposal, what is my inputs, what are my outputs, how do I communicate internally and externally, etc. And then you start abstracting, create different models for different data, create architectures in which you can even split domains through the hypervisor. So we can virtualize here. You heard of Docker, you heard of VirtualBox and these kind of things. Why wouldn't we put this here? So we put our real-time operating system because we heard it's something that we need. And we put Linux and Android running side by side. And we put some heavy middleware where we put our models. And then on top of that, we put all the applications, being that AI, being that media, being that our, let's say, driving assistance thing, etc. Looks pretty cool, yeah? And in these worker chips, if we lack any processing power, we can add more. We can add different dedicated worker chips. We add even more instances of the high performance controllers or different kinds of controllers. It can be, let's say, more dedicated accelerators for, let's say, camera vision processing, etc. If we even further lack the processing power, if we want to do something that is real time, that is processing intensive, that is bandwidth intensive, why not? We can add an FPGA and we can interconnect all this via PCI Express. We did this in personal computers. Why wouldn't we do this in the car as well? And of course, somebody told us that the safety is a very important thing for the car. So we add a safety chip so that we can do the diagnostics, so that we can figure out whether these guys are working correctly, and if not, to perform some safety functions. And this is where it pretty much ends, the understanding of a software guy, how the central vehicle computer shall look like. And it is really enthusiastic, so to say, to be here and to craft this. What kind of abstractions, models, and things are there? So it's all very, very great. And we can hardly wait to release the APIs to the programmers, to release the APIs to the outside world that somebody can take in the same way as if he or she were programming Android phone. So just imagine developing the app for the car in the same way you're developing the app for the phone. I guess I can earn my 10 years worth of salary doing and creating this probably. And if I partner with the tier one, so this is, let's say, a ZF Pro AI, they might package it into some kind of sturdy design and put this somewhere next to the right steering wheel, and I have the computer inside the car. So that's great. Yeah. But what are we actually solving here? So the autonomous driving is one problem. And the next, of course, is promise for my software stack. So this, what I just told you, is the American dream of my software stack. So I wanted to be able to do whatever I just described. So whether it is possible, let's see. So when I dive into the functional concept, the first thing is that I need to figure out what my computer shall be doing. Then there are much more smarter people than me, like Beher and Tongren, that did this decomposition of functions. And they said we need to have some sensing, external and internal, some model of the world. We need to understand the world to do the semantic understanding, localization, sensor fusion, then decision and control to do trajectory, energy management, platform fault management. We also do the diagnostics and then execute the trajectory and the safety. And this should be instantiated within my middleware, within my software architecture. That would be great if I could do that. Then let's see which autonomy levels are there. So probably you all know that we have 5 of them. So the first one is the driver assistance, in which the driver completely controls the drive. The second one is advanced driver assistance, in which the driver must monitor the drive. But sometimes we can drive instead of the driver, but the driver must keep the hands on the steering wheel at all times. Then even more relaxed scenario. Level 3, self-driving defined situation in which the driver must be able to retake if needed. So now the hands can be off, but the driver still must be there. If we beep, the driver must retake the driving. And the levels 4 and 5, where under some circumstances or all circumstances, we are fully driverless, so without the driver. And then we can, of course, see at which of the levels we need which functions that I just shown, and to figure out which use cases, which application are there. So just as one example, let's say traffic jam pilot. What does this mean, traffic jam pilot? So if you're in a traffic jam riding slowly enough, you can let the car move further down the crowded road on its own, one car at a time, without you needing to step on the paddle and release the paddle all the time. And it even would follow the lane and steer through the busy traffic. And this is the L3 function because it is slow enough and because you can retake when the traffic jam clears, you get a beep and you retake the drive. And this is one of the examples of level 3 functionality. But then to be able to qualify the solution, we hear about functional safety standards. They say, okay, you must adhere to ISO 26262. You must have some ASIL levels in mind, automotive safety integrity levels. And then you start reading through the standard and figure out there is some kind of table of safety levels that you need to evaluate your hazards. So let's say if I'm driving in my traffic jam pilot, is there a chance that I kill someone while I'm doing that? And then you simply need to estimate the severity, exposure, and the controllability of your situation. So severity means whether you can actually injure someone or not, like S0 to S3. If you can give a life-threatening injuries, then most probably, yeah, it's S3 is the most severe. Then the exposure means, okay, if the severity is such, whether I'm actually exposed. So this is the probability of a part of the probability of the situation. So can I actually do that to somebody? And it can say, okay, E0 is like almost impossible. So there's no hazard there. E1, very low probability, once a year. E2, few times a year. And E3 is actually medium probability once a month. And E4 is high probability at almost every drive. What does it mean? So if my traffic jam pilot is actually S3, I could kill somebody. It could also be, let's say, E3 if I encounter traffic jam several times a month and not every single day I'm driving. So it depends how we are going to rate the hazard. So how exposed we are to a situation that can harm us. And finally, we have the controllability. So if this situation occurs, if we can control it, if we can retake the driving, then it is C0 and we have no hazard again. But if it's a little bit harder to control, then the Cs can raise. And at some point, if there's, let's say, 1 out of 10 drivers that cannot control this and would allow the car to crash, then it's C3. And when we combine all that, we get the ASIL level. So the ASIL levels grow as these variables grow, of course, and ASIL B is the most strict. ASIL C is a little bit more relaxed. ASIL B is a little more relaxed. ASIL A as well. And QM means we don't have anything to worry about, basically. Just perform basic due diligence in the development. And when we figure out the ASIL for, let's say, a traffic jam pilot, then we come to something like this. If we have hardware, we need to adhere to some hardware level requirements. For example, our failure rate for different ASIL levels need to be along the lines of this. What does it mean 10 to the power of -8? This means that basically there is one in a 100 million situations that we can fail. So this is, let's say, the number. And when expressed in what hardware guys like, this is failure in time, fit, that is actually this number times multiplied by 10 to the minus 9, we get something more readable, like 10 fit, this is ASIL D, 100 fit ASIL B and C, and 1000 fit ASIL A. So if we have a hardware to design, if we can estimate the likelihood of the hardware failing, we can then match it with a hazard evaluation. And of course, each hazard is then again mapped and allocated to the functions that we developed and subsequently to the hardware blocks and software. Of course, we'll see about that a little bit later, that perform these functions. What about software? What does ISO 26262 says about software? Software, of course, cannot fail stochastically. So we cannot say 1 in 100 million times my software will fail, because actually whenever the software fails, there's a good reason why the software fails. And what ISO 26262 says, it says the software suffers from what is called systematic fault. And systematic fault means that it can fail only because of a very specific reason that is probably somewhere in our design. And ISO 26262 tells us how to design software to avoid these systematic faults. So there are 4 levels, ASIL A, B, C, and D, and the recommendations of different software development methodologies according to each of the levels. This is just one of the tables. There are tons of these tables. Whether we have a restricted use of interrupts, so that you cannot widely use the interrupts, whether we have the hierarchical structure of the software components, whether we have loose coupling between software components, whether we manage shared resources appropriately. So all these techniques that are further elaborated in the standard have the corresponding level of recommendation as per different ASILs. So of course, for the most hard one, ASIL D, everything is recommended. Let us say you should have it in a say it's highly recommended. And for ASIL C, B, and A, it gets more and more relaxed. So this is the, let's say, the way how this standard goes. And then I scratched my head figuring out that what about AI? They say systematic fault, but we all know that AI is pretty stochastic in reality, because we cannot figure out what is the function behind the AI because it was trained on some roads. Yeah. We trained it, we drove millions of miles with it, or hundreds of thousands of miles. And at one point we said, okay, it's trained enough, let's use it. And then we can say that for AI and AI-based software components, we can use the proven in use principle. This means that we must show that our AI is safe by showing the stats, showing the statistics and the failures that it caused. Now, the question is, can we correlate it with the reliability so that we can fit it back to the model and figure out the ASIL? So this is what is important. And this is where I conducted a very, very fresh research about it. And I will just give you a glimpse on what was the outcome. So to speak about reliability, we first need to know some of the basic terms, like the failure probability. And it all stems from the probability theory, of course. Failure probability means that at the time moment 0, the probability that our system is going to fail is 0. And as the time goes by, the probability rises, and at one point it will certainly fail. So this is the failure probability. Reliability is the opposite. So the reliability is 1 at the beginning, so it won't fail immediately, but as the time goes by, the reliability will drop. At one point, it will be 0. And if we want to, let's say, express it mathematically, we can say it has this, let's say, exponential connection with the failure rate. So this is the rate of our failure. The number of units that failed is some time interval. When we divide it with all the units that survived until that time interval, we get this magic number, this H, that can be integrated throughout the time to get the probability of survival, that is basically the reliability. So we can see here in this graph, so this red line can be the failure probability, sorry. So it's 0 at the beginning. At one point, it gets to 1. The reliability does quite the opposite. We can do the approximation and say, okay, maybe the failure rate is constant. So we can make the E system where the rule is strictly exponential. So we say the reliability drops and the failure rate, of course, the failure probability rises. But it is this strictly exponential law where we have this lambda as a failure rate assigned. So we have a little bit nicer graphs here that depict this. So reliability starts at 1, then exponentially it drops at one point after this many hours, it decreases to 0. Now, if I want to see how different components together make the reliability claim, I can simply multiply them. So if I have reliability for one component and for the second and the third and the nth component, if I multiply all those, I will get the total reliability of my system. However, the more components I have, the less reliable the system will be, because each multiplication essentially decreases the reliability. And the problem is, of course, if you have the low reliability on even one component, you will get a really low reliability as a product. One way to deal with that is, you probably heard redundancy. So add redundant blocks for some blocks. So if you add redundant blocks instead of this one here, for example, you will increase the reliability on this part here by simply performing this formula. I would not go into detail too much, but it is the way to increase the reliability of the total composite here is lower than the composite here, of course. Another way, you heard probably of the term diversity. So do the voting, they say. So instead of having only one component here, put 3. Each of them can have a different reliability matrix, so different failure rates, let's say, and they decide on the same fact in a different way. Then you have a voter that simply says, okay, if 2 out of 3 say A, I will do A, otherwise I will not do A. And this is how you actually calculate. Yeah, so these formulas are not for you to parse through, it's just the illustration so that you can see that there is actually a formal mathematical way in the reliability theory to perform redundancy and diversity and to get the final numbers. So if we take now the central car computer, so I actually was very bored, I would say, and created all this for the central car computer. So there's a tons of blocks here. So this is the only thing. So this is basically the image from the beginning, just dissected to all the components, hardware components that exist in the central car computer. Then if we take a performance unit, so like this one, and zoom in, we get to the software. So you have a lot of software here as well. This is the same software stack, my big fat software stack. And then I say, okay, some of the blocks may participate in some of the functions, some of the blocks may not participate in some of the functions. Let's see which blocks will affect my reliability in which of the functions and which will not. So if I skip all the heavy calculation, if anyone is interested into that, please contact me. I have a huge Excel files with all the numbers. So you must trust me at this point because we don't have time to go through this in detail. But the result, when you assume you have level 2 autonomy and don't use AI, so just plain systematic, for instance, software, and do hardware, what is at a hardware level available in this moment, you get something like this. This is the reliability of a central car computer. There are 4 functions here that were selected: informational functions using cameras or using all sensors, and driver assistance functions using all cameras or using all sensors. And the final is this blue line. So we can see after 5 million hours, it will be pretty long already. In total, when you fit the E-system rule here, you get the 630 fit. And if we remember, this is what? This is basically ASIL A. So this is the ASIL A level that can be only provided for the level 2 autonomy as a composite, so as a monolith without any decomposition and any funky stuff. Which ASIL do we actually need at level 2? So we can, of course, do the SEC, so these variables estimation to get the ASIL levels, and we get that we shall be, let's say for function 2, it's ASIL B. For function 3 and 4, it is ASIL C. So pretty much we shall have ASIL C at this point and level 2, but we don't have it. We got ASIL A. So what can we do about it? So we can try to do some funky stuff, like let's put triple redundancy at power supplies. Let's put dual redundancy at sensors, although we know it's very hard to pull off. We can put a dual redundancy at the item. Let's see whether we can go to that magic ASIL C, and we say that 290 fit. It is still a little bit too high for ASIL C. And then if we crank it up even more, that is actually not feasible today, we go with triple redundancy at item. We do redundancy at all the sensors. We even improve components by taking some of them by using Back to the Future movie for the components that don't exist. And we then can have 98 fit with ASIL C as a monolith. And now you can say, yeah, but on the roads, we have ASIL D, huh? What about that? So you're probably wrong. So it cannot be ASIL C in the future. It must be ASIL D today because we have level 2 controllers on the road. How they do it? They use a principle called decomposition, and they have additional block. They say, okay, central car computer and the domain controller cannot do it. I will have an additional block that will do the safety, and it's called disengagement unit usually. And what they do, they split the safety requirements, and they say, okay, so the most relevant safety requirement is going to be solely executed by the separate unit that is here, the disengagement unit. And disengagement unit actually says this. So in case there's any kind of failure and any kind of problem, I will, through the disengagement unit, allow the driver to take the driving operation and to, let's say, disengage the complete central car computer, the complete ADAS controller. And through that, you pretty much secure this. So the fallback here is the driver. So we say, okay, we have the driver is monitoring the road. If we can prove that the disengagement unit is at very high reliability level, it works at all times. And if I touch the steering wheel, it disengages my central ADAS controller immediately, then it might mean that I can use the decomposition to prove my ISO 26262 claim. So let's see, for the disengagement unit, it's much more simple. It's a simple controller, safety controller. You can take Oryx, you can take whatever you want. You take high reliability, very small piece of equipment, small controller. When we do the math, we get that it is at least ASIL C by design. It can be also even higher than this. If we'll take ASIL C at the disengagement unit, and we know that we got ASIL A for our monolith controller, in total, ISO 26262 allow us to sum up these two and to get ASIL D. So there's actually a chapter in ISO 26262 saying, if you need ASIL D, if you manage to argument the splitting of the safety requirements to, let's say, ASIL A plus ASIL C, we will grant you ASIL D. Okay, so this is how it basically goes. In behind, you have of course, the redundancy principle and the calculation behind it. But put in the simple terms, this is pretty much it. Now, when we go to level 3, if we take a look at the functions, traffic jam pilot, for example, we need to detect pedestrians, vehicles, environment, world mapping, sensing, whatever else. We say that the AI here is inevitable. And the question is, what we do now? Do we have any data? How do we actually prove the AI works? One resort that we can have it that I took the California driving institutions, driving board. I forgot what the driving motor vehicle, something like that, reports. DMV organization is called. And they ask from all the self-driving companies like Waymo, like Uber, like other self-driving companies in the US to report all the disengagements they have in the previous years. And this, what is good, and these reports are public. So I was able to download these reports from the DMV. So I download all the Excel files and put it into, let's say, Excel and plotted something like this. So what I got for Waymo for the last 4 years, I took the 4 years of driving. They expressed it in miles. So I did here, I converted it to hours by multiplying by 25 miles per hour, as in one study. To get the hours, I need hours for the reliability for my variables, and say, okay, how many disengagements in total? So they are piling up, but it seems like this curve is flattening. So the Waymo gets better and better, but it's not quite sure whether it's flattening or it's not flattening. Maybe it's going logarithmically up there. I'm not sure what is going to happen. This is where we are today. This is where we were actually 4 months ago. So it's pretty fresh. So now, we need to figure out, is there a trend? So how do you figure out the trend of that curve? And there's actually a whole field that I figured out that exists for software. It's called software reliability growth models. It's called SRGMs. And when I sifted through them, I came across the finite and the infinite ones. The finite ones are actually logarithmic and the infinite ones are pretty much exponential. So here I have these shaky one. This is the actual disengagement data. And these, let's say, nice ones are the SRGMs. And here I have Musa Okumoto, Goel Okumoto, have Riley, and have log power. So these are four versions that I selected that perhaps describe this in the best way. And I, of course, fitted it using software and calculated errors. And the candidates are these three. So Musa Okumoto, Goel Okumoto, and log power. So these three are pretty much describing these trends the best. However, we can see that the most accurate one, this one here, yes, no, this one here is the most accurate, log power, the red one, actually goes towards the infinity. And it says it will never plateau. And we would like it to plateau, yeah? So what can I do about it now? So you can see that the different behavior over time. So this is the logarithmic scale. So if we approximate the failure frequency with lambda, so with the failure rate, we need the failure rate to drop so that the reliability will stay somehow steady dropping. So not dropping very, very fast. So we can see at one point in time, after I don't know how many hours, these will be, let's say, low enough. Now, how low? Let's see how long. What we need now, we need 1.09 fatalities per 100 million miles. So this is what the statistics say that happens currently. So we need something around the ACLD level, in fact. And if we convert these miles into hours, we get a failure rate of approximately 3 times 10 to the power minus 7. And I started with this value, to be honest, and to figure out after which time our models are going to drop below this number. And voila. So if we have a fleet of 100 cars, and if we assume that Musa Okumoto is the correct one, we'll need 730 years of test drive. If you have a fleet, if the Goel Okumoto is the correct one, but this one plateaus almost immediately. So this is the exponential one. And this one had a very bad, very big error. So most probably it's not accurate. Then it will be just 7 months. But if we take the most accurate one, this log power, we get 11,000 years and say, okay, let's crank up the fleet. Can I have 1,000 cars in the fleet? And it's probably be 1,000 years. Okay, it's doable, maybe, for the fleet of 1,000 cars. How big the fleet currently is in Waymo? About 40, 50 cars, 100 cars. They need to crank it up a bit. The practical matrix is something that, let's say I said, okay, let's see. These three look a little bit strange. It's a bit too much. This one is not accurate. These two are probably more accurate, but come on, 10,000 years. Is it possible? And then I said, okay, this is how I could wait. I could wait for 50 years for the fleet of 100, or let's say 5 years for a fleet of 1,000. This is a guesstimate. I would say, okay, let me try with this. And let's see what happens when you try to model the AI component. While assuming it is constantly improving, it is trained as long as needed, either for the time that we saw in the previous table. So I can train it for this long, or I can train it for this long. I took these two numbers, like this one and this one. Let's take one realistic and one, let's say, practical. And let's see the reliability. Now, what we can do further, we deploy it after we trained it until the desired level. And when we deployed it, then I measure the reliability of the complete composite. How I struggled with the, let's say, I don't know which model is this, but then I said, okay, I can take the diversity principle. Let's imagine I have 3 AI components, and each AI component runs one side by side, so to say. Let's take the 3 that are these 3, let's say Musa Okumoto, Goel Okumoto, and log power. So these 3 models, we have 3 AI components. They use the diversity principle, majority voting, and this is one composite AI component. So I took all the models at the same time, basically, that were anywhere near the expected accuracy. So this is what I got. So these are the, these 3, blue one is the log power. So it drops pretty fast, as you can see. This is just the AI components, not the central car computer yet. We have the orange one, it's Musa Okumoto, so it drops a little bit slower, and the Goel Okumoto is something similar. Sorry, the Goel-Okamoto drops a little bit, yeah, much slower because this is the unrealistic one, the exponential one. This orange one is the Musa-Okamoto, and the yellow one is actually the diverse. When I put all three together, I get the yellow one. When I put the majority voting principle at the end. So the yellow one is actually the reliability that I have for the AI component. If I take the long training time of 730 years for 100 cars, if I take 50 years for 100 cars or 5 years for 1,000 cars, I get something like this that is not nearly as efficient. So you see, you immediately can count these zeros. That's very bad in reliability if you can count zeros immediately. Let's see further. Now, if I put it into L3 AI in the central car computing context, now this is the hardware that I need, the software, of course, that is systematically evaluated, plus the AI-based reliability. And I say, okay, this is an ideal world where I don't have any problems. I can source the components that I like. It's pretty much present day situation. And I get 1,480 feet. So this is not even the ASIL-C. This is not nearly the ASIL-C. So this is not even the ASIL-A. So I need to crank it up a bit. So if I do the triple redundancy, I put some more, let's say, tweaks, I can get 1,230. But all this is for the unrealistic time of 730 years. If I want to do the training in 5 years for 1,000 vehicles, then I'm not good at all. Then I have 8,000 feet. This is not nearly close enough for the monolith. So how will I ever do L3? So this is the problem with AI. Can we crank it up? So if I do 730 years of testing, I could reach ASIL-C in some kind of disruptive configuration after too much time. Let's say this is for the practical one actually, but this is an unrealistic configuration. Even if I do something completely wide, like the redundancies of 6 times here on the item level, at the best possible case, I can reach 690 feet with 6 times the redundancy. And we see that after the 6th, yeah, it gets less and less efficient. It cannot go below 100. And I need, if I take ASIL function table at level 3, I need ASIL-D in many cases. Here, I don't have even ASIL-B. It's bad. Can I decompose it again? This is a bit harder now. I cannot use the disengagement unit because I can leave the driver completely not grasping the steering wheel. So he can be reading newspapers. We had crashes in a similar fashion. Like if we take the traffic jam pilot now as an example, the driver is not as attentive as in ACC, in the adaptive cruise control. But let's try. Let's say that we split the safety requirements to 2 requirements. One is the vehicle must monitor and attract the attention of the driver if inattentive while performing traffic jam pilot. And when I evaluate this according to this criteria, I get ASIL-A. And then say, of course, the original one, the TJP must be disengaged automatically based on driver command or other defined failures. Of course, this says you must disengage it. And based on the evaluation on the fatality, on the hazard, you get ASIL-C. But then you get the disengagement unit, you get ASIL-C. But the general TJP function is ASIL-A. So I could decompose this if I'm really creative to ASIL-C plus ASIL-A, and then get ASIL-D again. So this is a voila solution, but the decomposition is not that easy because you must argue that actually you are able to use the disengagement unit that has, let's say, and to say that the rest of the system is pretty low in ASIL, because you need to attract the driver somehow, because the driver is laid back. So you need to beep, you need to do something wild to the driver in order to attract it and to be able to argue that you can have this kind of decomposition. And this is only for the traffic jam pilot. For all other cases in L3 autonomy, you need to try to do the same. And it's very, very hard to make a convincing argument at this level and to do the decomposition. But it is possible. It is very hard, but it is possible. So L3 makes decomposition really hard. And what about L4 and L5? You imagine already the story. So if we did the numbers, Can we use the decomposition here? So we don't have disengagement. Why? Because we don't have the driver. No disengagement means you don't have anything to disengage to. So if you have the driver, you can disengage to the driver. If you don't have the driver, you don't have the fallback. Do we have any other fallback? You can think about it. If I have a specialty vehicle driving on a well-marked road, maybe I have a fallback. Maybe I have another set of redundant sensors that could stop the vehicle. But in our passenger vehicles, this redundant fallback would be pretty much doing everything the same as in the original decision, because we don't have any better systems to decide instead of humans. So if you don't have a human, effectively, it's very hard to have any fallback. Yeah. And we need ASIL D. And our controller, again, it's a monolith at ASIL A. No disengagement. So we are stuck with a controller at ASIL A because we don't have disengagement. It's hard to decompose. Maybe somebody would invent some clever ways to decompose. It's extremely hard. So we have a monolith at ASIL A, and we need ASIL D, so it cannot be done. So this is the conclusion. So we did the math, and we got ASIL A for the monolith. We say the disengagement and the fallback is very hard. So the L4 and L5 are not possible anytime soon. So what can we do? We can resort to new standards and say, okay, let's forget about ISO 26262. It's too hard for us. So let's try to measure faults and not failures. Let's go to SOTIF, for example. You can look it up. It's a clever way to, let's say, circumvent the reliability theory. Or we can say as low as reasonable possible. So we can say maybe a little bit more people could die. Why not? That's the expected level of death that we can consume. It doesn't need to be that hard. So let's try to decrease these values a bit, so to see whether it's actually feasible. But then the question is, if we decrease the values beyond the values that we already have for the human drivers, what is the purpose of the autonomous driving? Limited scenarios. Maybe we don't need to drive everywhere. We will geofence. We'll be driving from point A to point B in a well-defined lane. We can have a well-defined infrastructure. This would drop the ASIL. Oh, it's possible, but this is not the urban pilot that we expect. Okay, so it's something different. This is a taxi, a bus in some kind of a built from scratch city. Formally correct AI. So we listened to a keynote today about formal methods. If we could formally prove that our AI is correct, we could, in fact, decrease this ASIL further, or increase the reliability of the monolith. Not until the ASIL D level, I'm afraid, not even with the formally correct AI, but we could try. It would be a good gamble. Is it currently possible? No way. It is completely impossible to prove that the AI is formally correct. Some AI, yes, but the AI in the world sensing, in the autonomous driving, it would be years, in my view. Somebody else could comment on that. And of course, while you're doing all that, you hope not to bury hopes in failed tests. If you kill somebody, like the woman in Tampa that was crossing the road riding a bicycle. So the AI didn't see her. So just killed her on the spot. And if that goes into the news, and it will, nobody would want to buy autonomous cars. If nobody wants to buy autonomous cars, we don't have money to make one. And we don't have money to make one, we won't do it anytime soon, unfortunately. It will be the same as not going back to the moon. So what about my software stack? So if I don't have monolith on the high enough ASIL level, how can I create my funky modules, my APIs, if I have disengagement units, even in L2 and L3, this is not a generic platform. So I need to devise disengagement. I need disengagement units. If I need disengagement units, I cannot create a funky application. I need to know every single thing in the cars to make an application. So this is not a promise that I was given when I entered this field. So how can I do that? So there are some things I could do. First, forget about your fancy software stack. Do not abstract too much. So don't spend too much time on abstractions, on modeling, on reusability. So focus on something else instead. On what? Focus on integration. So find better ways to integrate. Is the fact that you need disengagement units, you need different safety systems, subsystems. It will not centralize anytime soon completely. So we need to find ways to manage complexity and to perform the integration of the functions in more efficient ways. A lot of work for RTRK, TT Tech-Coda, and similar companies, I would say. Find good ways to manage complexity, of course. The immense complexity. Project management, how we do that, how we manage complex programs and projects. And of course, don't forget people along the way. So you need to have a good team spirit. A large team spirit, because you have a lot of team members. You will have thousands and thousands of people working on this. A huge team spirit. And of course, occasionally, you need to have a bit of fun, because in the end, we might have fully driverless vehicles in urban city centers. When? Who knows? If we work hard, stay disciplined, and be patient, the time will probably come. What concludes this presentation, actually? So I dared to perform some calculations, so probably some of them are wrong, but I think the overall idea is pretty correct. I cannot be off by that big offset, I would say. Okay, so thank you for your attention, and if you have any questions, we can address them at this point.
I have a question, please. You talked about functional safety, the safety of all the design of the central computer of the car that may be autonomous or semi-autonomous. What about wider concept of safety? For example, that central computer, I assume that will be connected to the internet, and then a hacker may get into the central computer of the car, introduce viruses, or make any other attack to the car. He may become the controller of the car. He can from remotely to control the car and cause an accident or any other things. That aspect of safety is considered by you?
Thanks for that question. So the security and safety go hand in hand. So let me ask by addressing two things first. So if you took a look at the presentation, I told you about systematic faults. So what I basically did, I said an impossible thing, in fact, that the software is free of systematic faults. All what I derived is the best case assumption that our software has no systematic faults, what is basically impossible. So the systematic faults need to be avoided by following strictly the ISO 26262. And only if you do everything according to the standard to avoid systematic faults and therefore avoid bugs that could be exploited for hackers, only then you can go into the field of reliability and calculate the reliability. So you're completely right. I did not take the security directly. I took it indirectly via the concept of systematic faults. And basically I said the systematic fault is something that must be carried out according to ISO 26262. We must do fault prevention and fault removal or fault tolerance or whatever on the systematic faults we can do. And if I put that into the equation, what would be a completely cumbersome and almost impossible work, you will get even lower numbers. So the conclusion is not going to be better. It can be only worse than what I just presented. But the security aspects are often overlooked, and you're completely right there, because they inherently are linked to the process. So how you develop software and how you protect information that you share among your colleagues. And if you have this level of complexity, huge teams, and you have one rogue engineer, so everything will simply fail. So your secrets are going to be revealed and the job is going to be harder for you. And yeah, I don't like to say impossible, but it's that hard at this point that it kind of, yeah, it goes into the impossible pretty much.
But if that important security subject is not dealt with, then all the idea of autonomous vehicles is not a good idea, I think.
Let's not be that dark. So it depends, of course, when you evaluate for safety, you need to know exactly which functions you execute. So if you say that the autonomous vehicle is the one that goes to the grocery store that is 1 block away and brings me my groceries, this vehicle can be autonomous. So it doesn't, I'm not inside, so my groceries are. I can drive 20 kilometers per hour or 15 or 10. So if I hit somebody, maybe nothing too bad will happen. Maybe I will injure somebody, but not kill that person. So for that kind of use cases, this, what I showed you here, does not actually apply. So you need to revisit. So I'm speaking about the passenger cars. I'm speaking about what we all expect about urban driving, about all these complex worlds. If you have a specialty use case, like in airports, you need to move bags from the airplane into the hall. You don't need that big ASIL levels, of course. So we could do the same math, get to the ASIL levels and see that the ASIL levels we could achieve with the monolithic configuration. Still, the security is going to be important, but not, let's say, not as important as in the cases where you carry people high speeds on highways. So this is for sure. So yeah, there are, I didn't say that autonomous mobility is going to be that. I said that autonomous vehicles, autonomous cars that we all expect are probably much further down the road than we might anticipate.
Okay, thank you.
Okay. Any other
Milan, maybe I have a comment, a short comment, and
yes,
maybe a question. So I'm glad that you found John Musa. Mm-hmm. Because I was involved in reliability software engineering for many years, starting from 1999, and then I think 5 or 6 years I was attending a major conference, IEEE, Software Reliability Engineering, and I met Musa in person. He's a great person. So he actually was working reliability software engineering for the Bell Labs telephone exchanges. The problem you're facing now, the engineers who were designing telephone exchanges faced. So how to have all these services and all the number of subscribers and scenarios and have figures that you are targeting. And so one of the paradigms is clean room engineering, invented by IBM, where you must do the formal verification. Mm-hmm. This is the first step. And then you have to have a clean mapping from the formally verified model down to the code, generated code, automatically generated code. This is, so our community, engineering of computer-based systems, is pretty much about that. So we model, we generate code from the models, we generate test cases from the models, and we do the both then apart from the formal verification, also the testing, which is a complementary guarantee that you met all the goals of the design. So using best practices from the past, which Silvia told us today very smartly, is that we go ahead. We don't go
this is
back.
One of
we
the
go
ways
just straight. We continue. The hardest part now is artificial intelligence and these deep learning networks, which we don't know how they operate. We don't have models for them. And that's the real challenge. If we want to use them, we have to somehow verify them. You know. And so, yes, the situation is very challenging, looking like almost impossible at this time. But this is opportunity.
Yes.
For the RTRK and for the collaborators. Thank you.
So basically, yeah, it was very interesting to figure out how many companies are actually doing these kind of domain controllers in different ways and promising different autonomy levels. Neither one of them speaks too much about formal verification. ISO 26262, let's say, roughly recommends, let's say, that you can select an abundance of other methods and not formal verification. So they don't limit, of course, the designs, because ISO 26262 intends to cover many use cases, not only the high level of autonomous vehicles. But yeah, the question is how to model. Even in the something that we can describe, is very hard to model, to create an accurate model. And even if for the cases of AI, yeah, you shared my view. So I will let the audience make their own conclusion.
Sylvia has a question.
Yes, hello. Thank you, Milan, for this very, very interesting talk. And I'm really very glad that you brought up the question of formal verification in AI. And Miroslav already commented the problem of formal verification in deep neural networks and other AI features. So this is really a long way to go. But I must say that teams intensively work on this challenging problem from very different perspectives, and we try to maybe follow some of them, but it's really it will take a lot of time and a lot of sources, different sources. So I'm afraid that for the rush of the industry and application, it's really a long way to have real formal methods and formal verification. But that's the story. We know
we have two options. One is to continue driving, maybe driving in a simulated environment and hoping that somebody would say, okay, this simulated driving is equivalent to the real driving, so we can maybe drive a little bit less, but still we need to drive. You saw the models. So if the Waymo drives for years now, and we see the curve, how it goes. So it's not plateauing yet. So it's mostly logarithmic. So it goes, you know, it will, if you take that data alone, it would be interesting. And I invite everyone who wants, just go to the DMV, take other companies, do the models. See, maybe some other company is better. I took the one that I believed is among the best. I don't know, maybe it will be vastly different for it. So there's a room for other papers, other research. But still, this route, if we go down this route and we do this 100 million something miles for years, and we end up not having the ASIL-D monolith still, then it doesn't make any sense. If you say the formal verification is going to be very, very far away, it's also a far-fetched thing, yeah? Mm-hmm. So it's the question whether we, but what is the bad thing in reality? So we have a demo car that works. We show it to people and it works. It runs 10 times, 9 times it goes without any problems, but this one time it fails, and it's 1 out of 10. It's way too much. It's way too much. We are speaking about numbers now about reliability. When you go into the reliability, demos doesn't count anymore. So you simply cannot. You know, it's a revelating fact that, and the industry simply So I am a software guy. So the reliability in programming different consumer applications is out of the question. So we figured out, okay, I must dive into that, because if I don't do that, I cannot go anywhere. Yeah. So this is why I put the title on the talk as I did. So to say, I'm not a reliability expert. I'm just a software guy that learned these things and tried to figure out where I'm at if I look at that from that perspective. And the results that I got are pretty, pretty strange. But not untrue, unfortunately.
Yes, thank you. But I also like this approach, your approach, saying, well, let's make cars for grocery, for the grocery. Well, one step at a time. I mean, we don't have to go immediately to the highways, right?
Yeah. So if you decrease the speed, you decrease the ASIL. So if you say I go 10 kilometers per hour, then the ASIL is achievable. So it's a very low speed. You are unlikely to kill somebody. So you can, so if you want your package delivered, it can run all night. So you don't care. So for these use cases, it already happens actually in the world.
Yes. Thank you.
Thank you, Professor.